Hello, welcome back. Here we have the first example of binary distribution. A binary distribution, like the simplest possible example is a coin flip. So I'm using that. In a coin toss, I will use 1 for heads and 0 for tails. And we call heads as success and tails as failure. It doesn't imply you want heads or head is better than tail, but it's just a label. It does not matter even if you change their names. And now suppose that you have a data of these 5 numbers. There are 5 numbers, 10100. Or you may read it as head, tail, tail. When you toss 5 coins, this is what you get. And from this, well, what is the probability of heads from those observations? It's simple. Just take a moment to try this question. And I will turn the page. The answer is 40%, zero point 0.4, because there are 5 observations and there are only 2 heads, 3 tails and 2 heads. So probability of heads is 2 divided by 5, which is 0.4. Simple. So yeah, binary distributions are simple. And now let's study the mean. What is the mean of these observations? It's the same 5 numbers. What is the mean? Also, take a moment. It's super simple. Just take calculating the mean of 5 numbers. Maybe take less than a minute. Stop the video if you have not finished it. I will turn to the next page now. 3, 2, 1. So the answer is 0.4 because the average is calculated this way. Sum all the 5 numbers. It's, by the way, remember how we calculated the mean. When you have raw data with a number of observations, then the average is simply adding all those observations divided by the sample size. So add all the observations, divide by the sample size, which is 5. So 2 divided by 5, 0.4. What I wanted to say here is, what I wanted to show you in this simple example is not about how to calculate the mean or probability, but I want to show that the probability of head equals to the mean. This is not a coincidence. It is an important property of binary distribution. So all the distributions in the binary distribution family satisfies this. So let's think about this, why that happens, why they are the same. So for any binary data, for any data of any binary observations of zeros and ones, so observations will be a lot of zeros and a lot of ones. And then when you calculate the probability of success, you count how many ones, how many successes in the numbers, in the data. So you have to count the number of success or the number of ones, how many ones you have in the data when you calculate the probability of success. But when you calculate the mean, you are adding all those numbers, you are adding all those observations. But when you add ones and zeros, adding zeros does not make any difference, so you can just drop all the zeros. So simply you are adding a lot of ones. And if you have 10 ones, their sum is 10. If you have 20 ones, their sum is 20. So sum of zeros and ones always equals to the number of ones. How many ones you have among those data. That's the main idea. So when you calculate the probability, you are counting the number of ones, and when you calculate the mean, also what matters is the number of how many ones you have. So in the end, these two are the same. The number of success, the number of and the sum of observations are the same. So therefore, the probability of success is defined as equals to number of success out of the sample size, And on the other hand, the mean expected value of x is calculated as the sum of observations divided by the sample size, and the numerators are the same because all the numbers are only zeros and ones. Zeros uh, and ones, like so when you have only zeros and ones, it's very easy to sum them because you are only adding ones and as many as the number ones. So by definition of the probability and the mean, they must be the same, always same. So that is one interesting and nice property of a binary distribution. And why does it matter? So now let's think about the mean. We have like from the beginning, I said 1 is a label for success, 0 is another label for failure. Um, it the number themselves do not have any meaning. It doesn't mean 0. So when you have tail, I write it as 0, but it doesn't mean there is not. It like 0 means nothing exists, but it it has nothing to do with tail. So tail has nothing to do with 0. So even if you change 0 and 1, still there is no difference in the analysis. You may just use different labels, so numbers have no meaning. Then the problem is when you calculate the average between zeros and ones and you get zero point 0.4, what is that? The number zero point 0.4 means nothing because 0 and 1 mean nothing. So still you can calculate the mean because 0 and 1 are numbers, but it means nothing. But so now I suggest you interpret the mean as the probability of heads, not as the average. So because zero point 0.4, there is no outcome corresponding to zero point 0.4, right? So there is no outcome between head and tail. So it's like coin stands up as much as like zero point 0.4 degrees. No, there is no outcome like that. So when you interpret the mean, you 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 may it may be better to interpret it as the probability of heads. They are equivalent. But still, the mean is important and plays an important role because later on we are going to learn a lot of statistical methods that is associated with the mean. So you can apply all the tools, all the statistical methods that apply to the mean. So uh, just everything like it is the mean. Zero point 0.4 is the mean, but don't interpret this as the mean. There is no outcome like zero point 0.4. You get what I'm saying, right? So okay. Anyhow, the key point is key lesson. To summarize what I said, the mean equals to the probability of success, and interpret the mean as a probability. That is, that's the first property of binary distribution. Okay, next, I'll think about another example. Multiple choice question. So think about your assignment. You have 10 questions, and each question has 5 choices. So you have to choose one answer from 5 options. And suppose that you randomly choose just whatever you want. Actually, the order of the choices are randomized. So suppose that you always choose the first option, first choice, A. Then what is the probability, then outcome from this experiment? You are randomizing you're experimenting your assignment. Then, and the outcome is whether you are correct or not. And I'm going to say correct as 1 and wrong as 0. So success, failure. In this case, success literally means you succeeded in choosing the correct answer, in randomly choosing the correct answer. So in this example, this is another example of binary distribution. And in this example, the probability of success is given by construction 1 over 5 because there is only one correct answer out of 5, and when you randomly choose one, the probability is 1 over 5. So we can write x binary distribution follows binary distribution with parameter 0.2. So this is the notation in this case. And or you may write it as a probability distribution in this form. Find the expected value of this random variable. I am going to stop this video here. Find the expected value first and then continue to the next video, please. Thank you.